So now we're going to take a little time to look at a specific kind of graph called a tree. And trees are simply graphs that have no cycles. So just to remind you, we know that a cycle is a circuit whose edge list contains no duplicates. And generally speaking, we're going to use C sub n to denote a cycle with n edges. So for example, here's a cycle with 5 edges. So this would be a C5. And the point is we don't want to have any cycles in a tree. So we can also say that this is not a tree. On the other hand, something that looks like this is in fact a tree, even though it's probably not the kind of tree you're used to. The idea for calling things like this trees is that when they were initially worked with, they tended to start and have a shape something like this. And now you can start to see why that might be called a tree. So just as we can have directed and undirected graphs, we can have trees that are directed or undirected. But in this chapter, we're mainly going to focus on undirected graphs. So as we've said, an undirected graph is a tree if it is connected and contains no cycles or self-loops. So this is another little addition. So it needs to be connected, so that means you need to be able to get from one vertex to any other vertex by following edges. And the second part says it contains no cycles or self-loops. So let's just have a look through these examples. So if we look at example 1, that's definitely a tree because it's not unconnected. It's got no cycles, no self-loops. So yes. Number 2 is also a tree, and so is number 3. But notice that when we have a look at number 4, we've got a cycle. So this is not a tree. If we look at number 5, we've also got some issues. In fact, we've got both problems here. We have 2 self-loops, and we also have a cycle. So this is definitely not a tree. Now, number 6 is interesting. Remember, we're looking at this whole thing as a single unit. And as we can see, because it's not connected, it's not a tree. However, each component is a tree. And when we have a graph like this, which has a bunch of separate components, each of which is a tree, we can call it a forest. Okay, so now we've got some intuition for things that are trees and what makes them not be trees. We might think about where is this useful. So a place where trees and sometimes graphs are often used is in chemistry, when showing diagrams of the atomic bonds. So there are certainly some compounds whose graphs are not trees, for example, benzene, but there are also many, like butane and isobutane, which are described by trees. And in fact, when chemists are wanting to do computations around molecular structure, they can use some of the algorithms which we will develop for working with trees. So here's a quick challenge. Draw all the possible non-isomorphic trees. So remember, by non-isomorphic we mean you can't move any edges and vertices around so that one graph it becomes another. So take a moment and sketch these graphs. So if we've got 4 vertices, we need to think of all ways that we can connect these vertices and still end up with a tree. So maybe the first one to think about is we could just do this. Now I've connected all the vertices, so this graph is connected and I don't have any self-loops or cycles. So this is definitely a tree. Now let's try and draw another one. So I'm going to keep my vertices in the same place, but I could also make sure that this is connected by using these three lines. And notice that there's no way that I could move the edges and vertices of the second graph in order to get this first graph. So these are not isomorphic. Let's think about, are there any others that we could do? Well, things that you might be tempted to think about would be something like this. But notice, if I switch these two vertices, then I end up with the graph that we had above. So really, we only have two non-isomorphic trees on four vertices. You notice that I didn't try and add any more edges in. If I tried to add in an edge here, I would suddenly have developed a cycle. If I tried to add in an edge there, I would have also added a cycle, and so on. So as I mentioned a little while ago, a forest is an undirected graph whose components are all trees. So you would look at this and you'd say, each of these things is a tree, but if we consider this whole thing as the graph that we're looking at, then it's not a tree because it has three unconnected components. So now that we have some intuition about trees, it's going to be useful to have different ways of computing whether a given graph is a tree or not. And we're going to actually look at 5 different ways of saying that G is a tree. So we're going to start off with saying we have a graph which has a vertex and an edge set. We're making sure that it's undirected and it has no loops. And it also has n vertices because the size of the vertex set is n. So this is saying we have n vertices. We're not going to do a rigorous proof of this, but I am just going to talk through it because it will give us a little more insight into the difference between any old graph and a tree. So the first thing that we have is that G is a tree. And we know that G is a tree if it's connected and it has no self-loops and it has no cycles. So how do we move from point 1 to point 2? So let's assume that G is a tree. So I'm doing a proof that G being a tree implies point 2. So point 2 says we want to know that for each pair of distinct vertices in V, there exists a unique simple path between them. So we're going to assume that G is a tree. Whoops. And we'd like to prove 2 from this. Well, let's have a look. For each pair of distinct vertices, there exists a unique simple path between them. So suppose that we don't have a unique simple path. So let's first check. Suppose that there is no path. Between 2 vertices. But then that contradicts the part about our G being connected because G is a tree. So this contradicts the other option that we have is we could suppose that there are 2 paths between some 2 vertices. Well, if you think about what will happen then, so I've got two vertices and I have two different paths between them. So here's a path and here's another path. Well, that contradicts that our G was a tree because it's supposed to have no cycles. So this contradicts our no cycle rule. And so you can see that we have proved that if we have a tree, then it must be the case that for each pair of distinct vertices, we have a unique simple path between them. So we've proved that being a tree implies point 2. Notice I didn't have to do anything about loops because we're picking a graph that has no self-loops. So we've ticked off each of the conditions for being a tree and made sure that it implies 2. So now let's show that if we have statement 2 being true, so for each pair of distinct vertices in V there's a unique path between them, let's show that that implies 3. So we're going to assume that 2 holds. And what we need to show firstly is that G is connected, and then we need to show that if we've got an edge in our edge set and we remove it, then what we end up with is a disconnected graph. Well, it's easy to see that G is connected because 2 says for each pair of distinct vertices in V there is a unique simple path between them. So 2 implies that our graph is connected. But then thinking about removing any edge from this graph, notice that because we have only one path between any two vertices, as soon as we remove one segment from that path, one edge, then those two vertices must be disconnected because there's no other way to get to them. So now we see that 2 and 3 are equivalent. So now we'd like to show that 3 implies 4. So we're going to suppose that we have a connected graph, which if we remove any edge becomes disconnected, and we want to show that our graph contains no cycles, but by adding one edge you create a cycle. So we have a connected graph, and if we remove any edge, then it becomes disconnected. So we know that we look something like this. And 4 says G is connected. And 3 says G is connected. So now let's look and see how point 3 can be used to show that point 4 holds. So let's just check. So we're assuming that we have a graph that is connected, and that if there's an edge in our edge set and we remove it, the result is a graph that's disconnected. And we'd like to show that this means that G contains no cycles, but by adding one edge you create a cycle. So we're going to assume that our graph is connected. We're going to assume that 3 holds, so it's connected and removing an edge disconnects. So the first thing we need to do is show that G contains no cycles. Well, let's suppose that G does contain a cycle. Then if we think about what our graph looks like, here's a very simple graph that contains a cycle. But we're also assuming that 3 holds, so we're assuming that if I remove an edge, then my resulting graph will be disconnected. But notice, as soon as you have a cycle, removing any edge, removing any edge does not cause the graph to be disconnected, because if you have a cycle, you have at least two ways to get from one vertex to the other. So any edge that you remove it's just going to mean you have to take the other path. Okay, so we've shown that G also contains a cycle. And now we want to check that by adding one edge, we create a cycle. So so this is a contradiction. So now we want to show that if there are no cycles and also G is connected, but removing one edge means we're disconnected, we want to show that by adding one edge you create a cycle. Well, suppose you don't create a cycle. Well, if we have a look, we're assuming that 3 holds, so we're assuming that we have a connected graph and that removing an edge will result in something being disconnected. And we think about all the ways in which we can add an edge. Well, any of the ways we could add an edge is going to result in a cycle. There's no way that we can actually do this if assumption 3 holds. So that's not possible. So we've shown that assumption 3, which is that our graph is connected and removing an edge will result in it being disconnected, actually implies that our graph contains no cycles, and by adding one edge we will have to create a cycle. So far we've shown that statement 1 implies statement 2, 2 implies 3, and 3 implies 4. And what we're actually going to do now is show that 4 implies 1, and then I'm going to leave 5 for you to discover in your own time. So we're going to assume that G contains no cycles, but by adding one edge you create a cycle. So we're going to show that 4 implies 1, we're going to assume no cycles, but adding an edge is going to create a cycle. And we want to show that G is a tree, and remember that to be a tree you need to be connected, you need to have no loops, and you need to have no cycles. So we don't actually have to check that our graph has no loops, because we said right at the beginning of the proof that we have no self-loops. So that's not something we need to check. And because we're going from point 4 to point 1, we assume that there are no cycles. So we don't have to check that there are cycles. So the only thing that we really have to prove is that if 4 is true, then the resulting graph is connected. So let's think about it. If the graph was not connected, so for example we had something like this, then adding an edge from here to here would not result in a cycle, and therefore 4 wouldn't be true. So if G is not connected, we can add an edge and not create a cycle, which contradicts 4. So we've proved that G is a tree. So for proving 5, I suggest that you use the previous 4 and see if you can do this with induction. Now we're going to have a look at some of the applications of graphs, and in particular the applications of trees. So here's an example that's actually a real life example. The Tertiary Education and Research Network of South Africa is responsible for providing all South African universities with high-speed internet. So here we've got a map of South Africa, and it's got all the universities. It's also got things like the Square Kilometre Array and the SALT telescope at Sutherland. So these are all the places that would like to be provided with high-speed internet. And as you can see, there are many lines joining them. So this is a fabulous example of a graph. Notice that it's definitely a graph and not a tree, because if we start at East London, we can make a full circle round back to East London itself. And there are some other circuit cycles as well. So one of the questions that might have been asked when TNet was being built was, what is the minimum number of connections needed so that each campus can have internet? So to start off with, we're going to look at a simpler example. So imagine we've got a university and it has 4 campuses, and the university administration wants some way for each campus to be able to communicate with any one of the others. So one option would simply be to create a complete graph on 4 nodes, and which would look something like this. And that would definitely solve the problem. Everybody would be able to communicate directly with everybody else. However, costs tend to be a major factor in building things like networks. So it's worth spending some time thinking about, could you get the same effect, but with fewer lines, with fewer edges? And of course the answer is yes, assuming that your connections can work through more than one campus. So for example, if we wanted to connect the West Campus to the South Campus, we could send the message from West to North and then from North to South. And in fact, if you wanted to connect West and East, then you take that same route and then send the message on from South to East. And in this way, you see that you can actually communicate between any 2 campuses, but we've only used 3 edges. So this is the kind of thinking that goes into optimizing networks. And the thing that's kind of fascinating is that it turns out that the solution to both the TNet problem that we saw and also the simplified version are trees. And this is in particular trees that include all the original vertices. So if you cast your mind back to when we were talking about graphs, we said that a spanning graph was a graph that includes all the vertices of the original graph. And now we're using a similar idea. We're calling a spanning tree is a spanning subgraph of our original graph G that is a tree. So there are a few things to note about a spanning tree. So if V is our original vertex set from the original graph, and E is the reduced set of edges which give us our spanning tree, then we can tell that the number of edges in our spanning tree must be the same as the number of vertices, minus 1. If you think about this, you can just draw a sketch to convince yourself. So here's a spanning tree, and we have 5 vertices and 4 edges. The reason that we use spanning trees and their significance is that when we look at a spanning tree, a smaller set of edges would not span the graph, while a larger set would have a cycle, which means it has an edge that's superfluous. So spanning trees are kind of the most optimizing thing we could pick when we're trying to reduce costs and create as few edges as possible in a network. So there are plenty of algorithms to compute a spanning tree for a connected graph. So notice we're saying connected here, and if you have a disconnected graph, then you'd need a spanning tree for each of the components. So let's have a look at just two algorithms. The first one we've got is a vertex-centric algorithm. So the idea is you take your connected graph. So here's some connected graph. Notice that it's got some cycles. I'm going to label the vertices, and let's work through this. So pick an arbitrary node and mark it as being in the tree. So just for fun, I'm going to pick B and say this is in the tree. And now we have a step that we're just going to repeat until I've found all the nodes that are going to be in the tree. So here we go, we pick an arbitrary node in the tree. Well, at the moment we've only got one, so that's B, with an edge to a node W that's not in the tree. Okay, so I've got an edge here to a node A, which is not in the tree. So the rule says we're going to add this to our spanning tree, and we're going to mark A as in the tree. Now we haven't marked C, D, and E as in the tree yet, so we need to repeat step 2. So we pick an arbitrary node in the tree. Well, this time I'm going to pick A as being in the tree, and we want to pick an edge to a node that is not in the tree. So I'm going to pick this edge between A and C, and I'm going to mark C as in the tree. And we're still not done, but now I'm going to take B as my starting point, and I'm going to take this edge here down to E, and I'm going to mark E as in the tree. Now notice, if I pick B as my starting point again, I don't actually have an edge that I can travel along to get to a vertex that's not in the tree. So I'll have to pick something else. You'd find the same problem if you picked A, but if you pick C or E, so let's just pick C, then we can take the edge that joins C and D, and we can claim that D is in the tree. So now we have our spanning tree for this graph. So let's just sketch it out. We've got A goes to B, B goes to E, A goes to C, and C goes to D. So notice that if we unfolded, so just be a little careful, this isn't a crossing. I mean, it isn't a node, it's just where two edges happen to cross because of the way I've drawn the graph. But I could actually redraw the graph by moving point A over to here, and that would take that crossing away. So it is definitely a tree. So if you think about how many times we had to do this, we did the process n-1 times because there are n-1 vertices that have to be added to the tree. So really what this algorithm requires is that you can efficiently find a qualifying vertex to add. So notice if we'd started at A and B for our last example, we would have had two cases of saying can't find a final vertex in A, can't find a final vertex from B, and you can imagine with a big graph that could take a long time. So we won't really talk about this, but one needs to think about how to efficiently compute a qualifying vertex to be added to the tree. So this was our vertex-centric algorithm. We were picking vertices and then edges. Now let's try a second algorithm, which is called edge-centric, so it focuses on edges. So I'm going to use our same graph that we had before. And let's work through this algorithm. So the idea is that we start out without any edges. We just have the nodes that are in the original graph. So notice that we can think of these as singleton trees. They each have exactly one node. And then as long as we have more than one tree, overall, we need to connect two trees together with an edge in the graph. So we can just start in any order. So I'm going to connect A to B, and I'm going to connect B to C. So now I've connected the AB tree to the singleton C tree. Let's connect E and D. And now we have a lot of choices. So we could connect A and D like that, or we could connect B and D like that. Or if we wanted to, we could connect C and D, because we have to connect the ABC tree with the E tree. So there we go. So that's another way of computing a spanning tree. So edge-centric and vertex-centric are our two algorithms we've looked at. So it's often the case that we're not just looking to, for example, minimize the number of edges. There might be other constraints that are important. For example, you can imagine that the cost of each line in the network might depend on factors such as the distance, and possibly whether the line has to be overground or underground, in which case that will affect the tree that you pick, because we want the tree whose cost is as low as possible. Another objective might be that you find that communication, if it runs over multiple lines, is noisier as you get more lines. So it could be that it's not optimal to have to connect to if we want to connect west to east, to go through north, south, and east, because that's got 3 lines and it might really degrade the signal. Oops. So we might have an objective that we want to select a tree with the property that the maximum number of lines that any pair of campuses must use to communicate with is as small as possible. So that will also change the spanning tree that we pick. So just to think about these two objectives, solving objective 1 requires what is called the minimal spanning tree. And this is where we use the idea of weights that we mentioned before. So we have an undirected graph, and it's got weights. And we call a minimal spanning tree, it's a spanning tree, so it has all the vertices of the original graph and edges that will connect all of the vertices. And then we pick the spanning tree, because there might be many spanning trees, for which the sum of the weights of the edges in that spanning tree is as small as possible. So that is solving our question of the tree whose cost is as low as possible, because we have the cost of each bit of the network, and we're going to pick the spanning tree that minimizes that cost. And if you're interested, Prim's algorithm is the algorithm to use to solve that particular question very efficiently. So you can check this out in the textbook. So now we want to think about solving objective 2. So we want to minimize the distance between any two vertices. So this is called a minimum diameter spanning tree. So again, we start with a connected undirected graph, and we find a spanning tree, so same vertices but a smaller number of edges, such that the longest path in T is as short as possible. So if we have the complete graph on 5 nodes, as we have here, so this is K5, it's very easy to create the minimum diameter spanning tree, because you pick one vertex and you connect it to all the others. And then at worst, to get from one vertex to the other, you have to go through 2. So if you want to connect V3 to V4, you'll go back to V1 and then out to V4. So you have really 2 links is the most you ever have to do. So if you want to create the minimum distance spanning tree for incomplete graphs, you need a two-stage algorithm. So the first idea is to locate the center of the graph, and the maximum distance from a center to any other vertex is as small as possible. And once you've got the center, then you do a breadth-first search to construct the spanning tree. So this actually brings us to the end of the content for this course, and I hope you've enjoyed it. Please spend some time over the next couple of days looking through the course material, and if you have any questions or areas that you'd like me to clarify, just drop me an email and I can make some extra notes or extra videos as the case requires. And good luck for the exams.